Okay, welcome to the class, and we have been discussing this DMRS, and we discussed this type A and type B DMRS structures, and we are going to recapture them, and then we are going to conclude this discussion by telling you that how all these structures are actually specified in the standard, and then we'll move on to into further details, into discussing further details of this. Okay, it'll become clear what are the remaining details and then when we see them. Okay, so is a quick summary of whatever we saw in last two classes. Okay, so if you recall, this type A DMRS is basically where PDSCH occupies most of the slot. Okay, and it comes always in the beginning of where the PDSCH data comes, and it is. So you see here the first DMRS is located in symbol 2 of the slot. Okay, that's where this PDSCH is beginning. Now in type A mapping, okay, this DMRS location is mapped relative to the start of the slot boundary. Okay, so this is the start of the slot boundary, and type A location is mapped according to this. Okay, we saw this type B is slightly different. Okay, there is a reason for that, and this LD is the duration between the first OFDM symbol of the slot and the last OFDM symbol of the scheduled PDSCH resources in the slot. Basically that's the mapping. Okay, that's where it is beginning from, the slot beginning, and LD tells us how many, for how many symbols this PDSCH is scheduled for this particular user. Okay, right. So, and then what will happen here is this user will estimate the channel at symbol 2 and use this channel estimates for other symbols. Okay, right, if this is what is happening. Okay, but standards it provides us a lot of flexibility, and then we saw this kind of flexibility wherein this DMRS can span over 2 consecutive symbols also. Okay, and this kind of these 2 symbols, when it is you extend it over 2 symbols, it helps us in defining many more ports for the DMRS. Okay, so this 2 symbols definition is used for defining higher number of orthogonal DMRS ports. Okay, right, and then we discussed this additional DMRS occurrences for type A single and double symbol DMRS. Okay, right. So, and what were those cases? It was for single symbol DMRS, there is we discussed the case when up to 1 additional single symbol DMRS can be transmitted. Okay, and in which case it can be transmitted where the PDSCH duration LD is between 8 to 9 symbols. Okay, so that was the case. Okay, so only 1 additional occurrence is allowed. Okay, and it is allowed if this duration is between 8 to 9 symbols. It doesn't mean that it will always be 2. There can be only 1 occurrence also. Okay, this is additional occurrence, and this is the base occurrence. Okay, which is at least 1 DMRS will always be transmitted. Okay, and so the first DMRS location is 2, and the additional DMRS is located in L bar is equal to 7. Okay, right. When discuss the case when 3 additional single symbol DMRS can be transmitted. Okay, and what was the PDSCH duration in that case? It was up to 13 to 14 symbols. Okay, and this is how it looks like. Okay, so if basically PDSCH is occupying the complete slot. Okay, look at this. This is 1 additional occurrence. This is 2 additional occurrence, and there are now here 3 additional occurrences. This is the maximum. Okay, first one of course always comes at the beginning. Okay, now when there is 1 additional occurrence, it comes in the symbol number 11. Okay, so that this UE can interpolate between the channel between these 2 DMRS. Okay, so it estimates here, it estimates here. Okay, now what it tells us is that when you are transmitting these 2 additional this additional DMRS, so if user has to interpolate the channel, it has to wait for this DMRS, correct? Okay, so there it introduces a delay, but since the channel is changing, okay, UE will have to wait for this additional DMRS. Okay, and that is, you cannot help it because channel has changed. Okay, UE is moving, and if channel has changed considerably, and if these old channel estimates are used, which were estimated here, is going to lead to wrong decoding later. Right? It's better that since this additional DMRS is transmitted, UE waits for it. okay, and then does whatever it wants to depending upon the implementation. Okay. And if it is a fancy mobile, 50,000 rupees mobile, it would have implemented a very fancy interpolator, because that's the kind of processing power it has. Okay. And if it is a cheap 5,000 rupees mobile, it will basically, what it will do, it will replicate some of the channel estimates here, replicate some of the channel estimates here, and get done with it, because that requires a much lesser processing power. Okay. And so these ideas are applicable here also. Okay. That it could probably see if there is this additional occurrence, this is a second additional occurrence. Okay. Now it doesn't have to wait for this, it can start interpolating. Okay, so the delay is lesser, but the channel is changing much faster. That's why there is this additional occurrence. So, and these ideas get replicated. We discussed why this kind of allocation is slightly different from this. It is made equally distant. Okay, that's the optimal design, because there's all these symbols will see good quality channel estimates if these additional occurrences are equidistant. Okay. So that was the idea, that this 3 additional DMRS are located in symbols 5, 8 and 11, not 7 and 11. Okay, right. So we did not take this and simply copied one DMRS in between. We did not do that, right. Okay. So this is what we saw with respect to type A. Okay, and type A, if you recall, it is the most common mapping, because it is used for non-URLC kind of data. Okay, and basically this kind of data is scheduled in the beginning of every slot, and then the reference can be from the beginning of the slot. Okay, but this is unlike the URLC transmission, wherein the URLC can come anywhere in between. Okay, and for that the separate mapping type is defined. Okay, and it is used to support this URLC transmission. And what is this? So this is one example wherein the URLC is come somewhere in the middle. It can come at the end also. Okay, and it could occupy 2 symbols, right? So now that it has come, certain things change. The way this type B mapping is defined, it changes slightly. Okay, one is the reference number. Okay, the way this allocation is referred to. Okay, and so typically these URLC transmission occur over a small fraction of the slot, not the complete slot. Okay, and we know that URLC cannot wait for the start of the slot boundary. Then, as usual, DMRS is front loaded. Okay, it always comes in the as the first symbol of the data allocation. Okay, and this is the key difference with respect to how it is defined in the standard. The DMRS location is not given relative, is not defined relative to the slot boundary, but rather relative to the data location. It makes sense because for URLC, you are not tying it to the beginning of the slot. Okay, if you are not tying it to the beginning of the slot, why define it relative to the beginning of the slot? Rather define it with respect to where it is coming. Okay. Right, so LD is the number of OFDM symbol of the scheduled PDACH resources, and so this aspect is basically unlike type A transmission. Okay, so and we saw this. Okay, that if it is a single symbol DMRS transmission, if the duration, okay, PDACH duration is 2 symbols, then there is no additional occurrence. If PDACH duration is 4 symbols, there is no additional occurrence, right? Okay. Then if it is 7 symbols, 1 additional occurrence is, okay, right? And so then we did not cover this, but you see this, okay, then even if it is a double symbol, okay, so DMRS type B also can have double symbol, okay, but here you see this additional occurrence, okay, this even though this PDACH duration is 7 symbols, it is not, additional position is not allowed. Okay, if it is 2 symbols, okay, it is not allowed, and it is something similar to this, okay, wherein we just showed that, wherein if it is the duration is for 4 symbols, no additional occurrence is allowed. Okay, similarly here, if the duration is 7 symbols and it is the DMRS is of 2 consists of 2 symbols, then additional occurrence is not allowed. Okay, right? So that's where we stopped, but now we'll see how it is actually defined in the standard. Okay, so this is the table, okay, which is given in the standard. Okay, and that's how it is defined. So let's read through this carefully, and it will become clear what we are saying. Okay, so what are 2 different kind of mappings? Type A and type B, right? Okay, and this is the duration in symbols. okay, right. So where the symbol it can be like the PDACH duration can be in like these many symbols, okay. Now you see this, if you pick up, you go back and check, okay, that if the duration in symbol is 3, okay, then there is, you see that there is no additional DMRS is allowed, okay. It's only the base L0, okay, and which can come in. So this typically says that there is no additional symbol, no additional occurrence is allowed in all these cases, okay, right. You see this like how many, 1 2 3 4 5 6 7 8 9 10 11 13 combinations are there, okay. So base station can specify this using 4 bits, okay, that one of these configuration is allowed, right. And then so this is, you saw this, that's where if this is from what we saw at the end, that if it is 13 and 14 symbols, okay, the PDACH duration is 13 and 14 symbols, you look at this, okay, base is L0, okay, then if one additional DMRS is allowed, it will come at the 11th symbol. If 2 additional DMRS are allowed, it will come at the 7th and the 11th symbol, and if 3 are allowed, then it will come at these symbols, right, okay, that's how it is specified, right. And there is no counterpart for type B, okay, right, and this we are seeing for single symbol, okay, right. I will show you a similar table is defined for double symbol also, but then if PDACH duration is 12 symbols, correct, what happens then? Then if there is no additional occurrence, this is going to come at L0, and if one additional occurrence slightly different will come at symbol number 9, 2 additional occurrence will come at 6 and 9, 3 additional occurrence will come at 5, 8 and 11. They are same, but they are different because of the fact that the duration is reduced, right. PDACH duration is reduced, so there is no 13 and 14 symbol. So you basically you do these two allocations slightly differently, okay. So there are different combinations which are defined, and we saw some of them, okay. And this is we saw this, we like glossed over these one also, okay. And similarly they are defined for this PDACH mapping type B, okay, and this is URLC, okay, correct. And this again for single symbol, you see this, if the PDACH duration is between 6 and 7, then only there is this additional occurrence, correct. For all others there is no additional occurrence, correct. And if you look at this is not even defined. So what it says is that PDACH duration is basically, it's 5 symbol is not allowed, okay, for if it is mapping type B, right, okay. So that's what it says, okay, if you look at this table. Similarly, look at this was for DMRS position for double symbol, okay, and we saw this, okay, this was type A, okay, double symbol, and this is where this additional symbol can come. We saw this in detail, I did not touch upon it yesterday, but if PDACH duration is 14 symbol and DMRS is double symbol, first one will come at L0 and the second one will come at the 10th symbol, correct, okay. So again, so this is how these tables are defined, and that's how those figures were created, okay, right. And similarly you see this, that's what I alluded to at the end, if it is type B and 2 symbol, only I cannot see any other additional symbol being defined, correct, okay. That's the case we referred to at the end, okay, correct. Now these are basically the type A and type B, okay, DMRS allocation. Now these type A and type B are further divided into 2 different types, okay. It will become clear why they are defined like that. We will discuss that in detail. They are called type 1 and type 2, okay. And before we talk about type 1 and type 2, we basically these type 1 and type 2 they allow you to define different number of antenna ports, okay, in the sense that type 1 will have, with type 1 you can define fewer number of antenna ports than when compared with type 2, okay. And once you look at the structure of these 2 different types, it will become clear how these they are used to define different number of antenna ports, okay. So we will discuss this type 1 first, okay, but before that, again this is to put things into perspective, okay. Why do you need different ports, okay, and this is typically for MIMO transmission, okay, wherein like you are sending DMRS along with data, okay, and it's a like multi-layer transmission, okay. And in order for the user to estimate this equivalent pre-coded channel which the base station will use, the precoder the base station will use, and it will make the channel pre-coded. So user has to estimate that pre-coded channel, okay. So if you look at this, so the system model for pre-coded DMRS transmission looks something like this: y is equal to h p tilde plus n. Okay, we are talking about the DMRS phase, okay. And now this is HVP plus n. We are pretty comfortable with this, okay, the system model, and we call this HV as h tilde. Okay, this is the pre-coded channel, and we know that the dimension of this channel has reduced considerably, okay, because the precoder allows us to do that, okay. And now in order for this for the UE to estimate this h tilde, okay, so we saw that this precoder is of dimension how much? The precoder is defined for 2-layer transmission, okay, right. So if h is nr cross nt, the precoder is designed such that its dimension is nt cross nl, and nl in this case is, in our running example we are assuming it to be 2 layers, and this h tilde becomes nu cross nl, which is nl is 2, okay. So you need 2 orthogonal ports, orthogonal DMRS, okay. That's the idea, okay. I'm just recapturing that and assuming that channel remains constant over 2 subcarriers, and you will see this fact in defining type 1 and type 2 structures, which we'll see now. Fine. So this channel remains same for 2 subcarriers. Then what happens? The G node B will transmit first DMRS, which is the first port, okay, define something like this, okay, 1 1, okay, over the first subcarrier, correct. This is the precoder, okay, PA will be transmitted over the first subcarrier, and PB will be transmitted over the second subcarrier, correct, okay. Right. So how does this system DMRS look like on the first and second subcarrier? How will this be received? Okay. What will the system model? The system model will be YA will be h tilde PA plus NA. Okay. Right. YB is h tilde PB plus NB. Okay. Because you are looking at 2 separate subcarriers. That's how you are creating orthogonality. For defining 2-port subcarrier, 2-port reference signal, you need at least 2 subcarriers. Okay. And now you have gotten this, what happens? You stack them together. This is actually not given in the standard, it is all basic communication theory, okay. This is the receiver part, and then you put them together, each one of them is a column, okay, the column vector. You put them together, this is noise, and then it becomes a matrix, call this, okay. So you have taken h tilde common from here, and you call this matrix, this is a 2 cross 2 matrix, okay, nu cross and L matrix, okay, the 2 cross 2 matrix in this example, okay. And one key aspect of this matrix is that it's an orthogonal, square orthogonal matrix, okay. And we know how from this y how h tilde can be estimated. Just multiply y from the right by p Hermitian, okay, and you immediately get this, you will be able to estimate h tilde, okay. And we discussed this aspect in detail, like why this orthogonality is crucial, okay. I gave you a thought exercise also, wherein like if p is not orthogonal but linearly independent, okay, then how will this channel estimation work, okay. So, and we saw that it will not be that simple, okay. You can still recover the channel, I am not saying that, but it will not be that simple, okay. And you see these ideas being used in defining the DMRS, and that is what I am going to show you now, okay. Right. So that's what, so now this is something what we have not seen till now, okay. So look at this, what are we saying here? It's type 1 single symbol DMRS, right. We have studied single symbol and double symbol DMRS, type A and type B. Both of them have single symbol and double symbol, right, okay. So you look at this, okay. So this is one symbol, okay. That's why I like recaptured the DMRS transmissions. So look at where it is beginning, okay. It is a front loaded DMRS, okay, correct. So this is beginning from second symbol, okay, right. So now the first thing here is that this type 1 single symbol is defined for 4 orthogonal DMRS ports, okay, right. And what does that mean? Okay, that you can, using this type 1 single symbol, you can define maximum of 4 different orthogonal DMRS ports, and this figure tells us how they are actually defined. Okay, right? So you have to look at it carefully. Okay, so what does this mean? Length 2 orthogonal chord cover. This OCC is orthogonal chord cover. Okay, what does that mean? Whatever we used in the last slide, +1 and -1, right? First symbol was first pilot was +1, second one was +1 and -1. That's is called, the technical name for that is a code, correct? It's a 2-bit code, correct? And now see that you look at this, is it length 2, okay, 2-bit orthogonal chord cover. Okay, so you look at these 2 orthogonal ports. Okay, they are defined over same subcarriers. See here, this and how are they defined? They are defined over every alternate subcarrier. Okay, let me draw it over here. Okay, see, this is over every. Okay, I think it is easier if I point it here. Okay, so this, you look at this port. Okay, every port is given a port number. Okay, correct. So this is the port number which is given in the standard 1000, 1001. Okay, and what is it telling? Okay, these 2 ports will use the same subcarriers. Okay, look at this. Okay, so what is this? This is basically this is the pilot. Okay, for orthogonal, for the port number 100. Okay, and this, which resource element this port is using the even subcarriers, correct? Okay, right? This one is using the even subcarrier, every alternate 0, 2nd, 4, 6, 8 and 10th. Similarly, this is also using the same subcarriers, 0, 2nd, 4th, right? Okay. Now, how are they made orthogonal? That's what you have to see. Okay, they are made orthogonal by using this length 2 orthogonal chord cover. What are we saying here? I am just looking at this. If this and this. Okay, so look at this sequence. This is +1, and what is this sequence? +1 and -1. Okay, and we know that they are orthogonal, and this fact is repeated for all of them. So all of them are +1, ++, bottom it is +-, okay, right? Now you could ask me that for creating these 2 ports, okay, you need only 2 subcarriers. Why are you using all of them? Right? I said that you'll need, if you have to create 2-port DMRS, okay, you only need 2 subcarriers. Okay, so if you look at this and this subcarriers are enough to define a 2-port DMRS. Okay, correct? But we are using these subcarriers also for the DMRS. Okay, now, and same here. Okay, this is applicable for all of them. Now you are increasing the length of these pilots. Okay, so that you can get better noise averaging. Okay, what are we saying here? Okay, so you estimate the channel over this. Okay, right? If the channel remains constant, okay, so over these subcarriers, okay, then you can average them. Okay, so what does that mean? Okay, so you have just, if you assume that this channel remains constant over the entire this PRP, over entire 12 subcarriers. Okay, right? Now in principle what you could do is that, so your channel will remain constant. Okay, so you will estimate this channel at, let's say, this subcarrier, 0th subcarrier. Okay, so what you will get is H plus N1. Okay, this is the channel at 0th subcarrier. Okay, now channel at, let's say, 2nd subcarrier, again it is constant. Okay, so noise will be different. Okay, correct. So if you basically, what can you do? Okay, so if you simply do y0 plus y2 by 2, what are you going to get? H plus N1 plus N2 by 2, right? And we have seen this exercise, we have done this exercise earlier also, wherein you simply add the noise. Okay, the variance of the noise comes down by a factor of 2 when compared with the signal, right? So correct, so SNR improves by a factor of 3 dB, right? Okay, so that we have already seen. So that is, if the channel remains constant, okay, that's what you could do. But in practice, if the channel is not constant, okay, then you could basically, this channel is changing across the subcarriers. Okay, you need these additional pilots to estimate the channel across these subcarriers also, right? Okay, so that's what is happening. So you see this, that the DMRS are embedded in all the resource elements. Okay, and where they are not embedded, you either interpolate them and simply copy these estimates, so that you have the estimates available for these subcarriers also. Okay. So, it is based on like what kind of channel conditions you are seeing. Okay. So, you could either use them for improving the performance, okay, or you could interpolate the channel and find out the channel for these remaining subcarriers, okay, and that is what it is done over here. Okay. But you look at this, these sequences are basically they are defined over same subcarriers and they are orthogonal. Okay. So, these two ports are orthogonal using in code domain, that is what it means, okay, because how are you making them orthogonal? You are making them orthogonal using this length to orthogonal code cover, correct. Okay. Differentiate these two ports with these ports. What is happening here? How are these two ports orthogonal with respect to this? They are orthogonal because you are using different resource elements. They are orthogonal. These two ports are orthogonal with respect to these ports in frequency, correct, not in code. You do not need orthogonal code cover over when making these ports orthogonal with respect to this, okay, because they are already orthogonal in frequency, right. Okay. But within them, how are they made orthogonal? They are made orthogonal again using length to orthogonal code cover. See this plus 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 minus, and they are defined over same subcarriers, correct. Okay. That is why you did not define the subcarrier the DMRS for these locations for these two ports, so that you could define another two ports using these resource elements which were not used here. That is the idea, okay, right. So, if you do not look at all of them, okay, forget these subcarriers for some time, how many resource elements are you using to define 4 port DMRS? You are using 1, 2, 3, 4, correct, because plus these subcarriers, 2 subcarriers you are using for defining these 2 ports, and these 2 subcarriers you are using for defining next 2 ports. So, in total 4 subcarriers, okay. Another subcarriers you are using because there is a necessity to do that, because the channel is changing across this frequency also, these resource elements also, right. Okay. So, that is what is happening, and this is what I told you verbally, this is what is written for the record. So, antenna ports 1000 and 1001 use even number subcarriers in frequency domain, even numbers, okay, right, and use same subcarriers but orthogonal in code domain. That is what I just explained, okay, right. And so, this is called, so another technical term. So, antenna ports 1000 and 1001 belong to code division multiplex group 0. This is called group 0, CDM group 0, okay, because this is the 0th group, okay. And antenna ports 1002 and 1003 use odd number subcarriers in frequency domain. That is what I just mentioned it to you. And if you look at all 4 of them, okay, how are you ensuring orthogonality? You are using both frequency and code domain. These 2 are orthogonal in code domain, these 2 are orthogonal in code domain, but across 4 of them, across these 2 groups, how are they orthogonal? You are using frequency to create that orthogonality. So, if you look at all 4 of them together, what do you say? They are orthogonal in code and frequency domain.